Hi guys, BuildZoid here, and today we're going to be taking a look at the RTX 3090 Amp Extreme Holo PCB from Zotac. It's been a while since we've last done a GPU PCB breakdown. The pictures are from Tech PowerUp, Tech PowerUp's review of the card as usual, so if you want more details on it, you should check out the link to their review of the card down in the description below. And let's just get right into it. This is sort of like, I guess, it's not the bare minimum, okay? Like, the bare minimum from Zotac is, I don't even know what those cards are called, but yeah, this is not the bare minimum. At the same time, it's not really that amazing. It's basically a stretched reference card, very similar to the original 3090 FTW3 from EVGA. So, yeah, though we do have some nice, overclock. Well, the thing is, like, you probably shouldn't be taking this on LN2 as far as I'm concerned, but you do get some nice, this would technically be an overclocking feature, but here it's more like, well, if the card up and dies, this will make your troubleshooting process a little bit easier, won't it? But yeah, so you get voltage read points, and they've really just kind of given you all of them. I mean, you have a ground point there, you've got 5 volts, 1.8 volts, memory voltage, why do they have one of the 12 volts? I am very confused about that. Why don't they have all of the 12 volts? Because, like, there's at least 4 different 12-volt power planes on this card, and with how NVIDIA likes to make, simple things unnecessarily complicated, there's potentially more of them. I'm not really sure why we need a 12-volt underscore F. There's a 3.3-volt rail. I guess these are both from the PCIe slot, then, which I still don't get why you would need read points for those, but anyway, PEX rail, core voltage, and uncore voltage. So, yeah, MSVD is uncore, the lower portion of the chip. So yeah, we have some voltage read points, which are kind of nice. We have what looks like a BIOS, what looks like a position for a BIOS chip that they, like, BIOS switch that they decided not to use. Yeah, I can't really see that as being much of a lot. Well, I mean, technically you could take this card and then, like, throw one of the extreme overclocking BIOSes and hope that it gives you a higher power limit at the same time. I don't know. I don't feel like that's that much of a loss. So, anyway, let's talk about the actual power delivery here. Well, I guess you've got your 3 8-pins, then the ridiculous number of shunt resistors, because this is an NVIDIA card, and again, why would you just monitor the power going through each of your power connectors when you can just, like, I really don't know. Like, there's another one over here, right? And there's 4 power inputs, and there's 5 shunts, and at that point, you've already got to ask why. Because it's like this will monitor the PCIe slot. This will monitor, the other 3 will monitor the 8-pin power connectors. Got what looks like, no, that's a resistor. Okay, that's not a shunt. At least it doesn't look like that's a shunt. So yeah, we have a few too many shunts relative to how many actual power connectors we have, but that's nothing new for NVIDIA GPUs. We've got another one down here. Yeah, so this phase seems to just have its own current sensing dedicated to it. And we've got, that's a shunt. Yeah, R5, like, the thing is, the R is like 0.005. So this is a 5 milliohm shunt. That's a 5 milliohm shunt. How many more are there? I think that's it. I hope that's it. But anyway, so as usual for NVIDIA, we have a totally unnecessary amount of current monitoring because, like, I have no idea why they do this. Literally no idea. Like, this is solely an NVIDIA thing. And then a lot of the actual, like, some of NVIDIA's board partners will actually not bother to go do this because it's just, why? Why? Why would you need to have this much current monitoring when you've only got 4 power inputs? But anyway, yeah, so all of the shunts around the card are handled by this chip, and there's another one of these on the back. That's a US 5650 from UPI Semiconductor. I don't know if the data sheet for those is public just yet. But yeah, that's like a 4-channel shunt, like 4-channel shunt monitor. So it basically monitors the power going through each of the shunts, and then it reports that to the GPU core. And there's 2 of these because each of them only monitors 4 shunts. And as we've just highlighted, this card has at least 7. I think it's 7. I've lost track. Wait, there's another one here. 8. I give up. Screw it. There's a lot of shunts. Anyway, you've got another US 5650 on the back here. So the problem with this is, well, this is a big reason why if you're trying to like shunt mod modern NVIDIA GPUs, and I think they started doing this with the 20 series, this like crazy high number of shunt resistors, is that if you only mod the primary input shunts, the shunts later downstream still end up complaining about you pulling too much power. So you basically have to, so like if you go older NVIDIA cards, there's like 3 shunt resistors that you have to mod. On higher, like modern NVIDIA cards, you might be looking at having to mod like 8 of them, potentially. Because otherwise you end up like, because I've not had a 30 series card in person. They're very expensive. They're also not very common in the UK. So I've not had a chance to mess with this, but on the 2080 Ti, this was a real problem for me because I had a 2080, like I modded the shunts on a 2080 Ti. The card would report that it's not pulling that much power, and then it would still be power throttling because I hadn't modded like all the other minor shunts downstream the 12 volt side of the power delivery. So yeah, NVIDIA GPUs are just great with this. Fun fact, it's actually harder to power mod AMD, like hard mod the power limit on AMD GPUs is actually significantly harder because AMD just doesn't bother with shunts at all. But I don't know why we can't have the same, like why NVIDIA ever like went from what they had for say like 700 series, 800 series, 900 series, even 10 series was simpler in terms of the power monitoring than what they do on 20 and 30 series. But anyway, yeah, so, just NVIDIA 30 series things. And in terms of the power delivery, we've got a kind of a unique VRM layout here for a 3090 because Zotac decided that they aren't going to have, like, they decided to sort of group up the memory VRM a bit more than usual. So, so basically the top part here is vCore, which isn't normal. Normally this top phase would be memory power. Then over here we have, wait, I've highlighted this wrong. I'm looking at this like, what's wrong with this? It's because I'm highlighting just the inductors, which doesn't make any sense. So, anyway, what's kind of neat is you can really see the power plane splits on this card. Makes it really easy to tell which part of the VRM does what. That's nice. And anyway, so these 2 phases down here, this is memory power. Then this over here is MSVD. Actually, I'm just going to put that over there. So, or what I like to call uncore voltage. And then all of this up here is vCore. Also, notice how the vCore power plane has a trace that just goes off to the voltage read point. Basically, the reason I'm pointing that out is if you're pushing a lot of current into the GPU core, this thing right here is going to be measuring a significantly higher voltage than what the core is actually receiving. So this is more for getting a rough idea of like if you're going to volt mod the card and you want to see if the voltage is going up or down when you're tweaking your volt mod, it's great for that. For actually getting an idea of what operating voltage the silicon is at, it's completely bloody useless because you're measuring off of like some random corner of the power plane, right? Like this, like the only way this could be worse is if they were measuring from over here. If it was connected like that, that would be that would be about as bad as you could make it for making it look like you're getting way more voltage than you think you are. So yeah, it's just like, but hey, you do at least get like voltage read points are nice. And this is a normal thing for a lot of GPUs. Like I don't think many GPUs with voltage read points really put much like effort into getting like super near like, because the thing is, from the voltage controller's perspective, there's actually dedicated BGA connections on the chip to the voltage controller, so that the voltage controller knows exactly what voltage the core is at. And why should the end user know? right? There's no need for you to concern yourself with what voltage the core is actually at. This right here is perfectly acceptable. So, yeah, so that's something to sort of like. I just find it neat that it's really obvious on this card, because on a lot of other cards, it's the same thing. There's a voltage read point like somewhere in the power plane. Who the hell knows where? And then when you go to use the voltage read point, it's like, whoa, I'm measuring a really high voltage compared to what the voltage controller is reporting. Not that the voltage controllers on this card are going to report anything, because they're analog. We're going to get to that. But yeah, on some cards, it's like the voltage, like a lot of voltage read points are just not super accurate on GPUs. So yeah, and here we have a very clear, visualization of why that is. Because they just kind of grab it from the power plane, which is like, well, yeah, that's not a great place to measure your core voltage if you want any, as a rough indicator, fine. As for accuracy, useless. Anyway, so that's this side of the card. On the other side of the card, we have a far more normal VRM layout, which, wait a minute. Memory, okay. Ah, yes, okay, I was just confused by the two capacitors. Okay, well, we're going to do it from the bottom, because from the bottom it's easier to keep track. So this right here is more MSVDD. Then above that, we've got one phase of memory power. So we've got more VMEM. And then above that, we've got just vCore. Nope. Up to here, we've got vCore. And then above that, we've got more memory power. So this is like... So the thing is, on most RTX 3090s, you would have memory power actually like here, 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 and here. And Zotac has gotten rid of this top phase up here. Or more like they've moved that phase down here, which I guess simplifies the layout of the PCB for them. But theoretically, it might mean that you're going to have a low voltage spot in this area of the memory. Like these two memory chips right here might end up getting slightly lower voltage. Like, well, no, slightly lower voltage you're going to get even on like this chip relative to this chip. Like the further away a memory chip is from the actual VRM, the lower the voltage is going to be on it. But there's going to be potentially a bigger difference on these two chips on this card relative to what you would see on other cards, which could translate into ever so slightly worse memory overclocking. So yeah, that's why normally you see RTX 3090s have the memory VRM really sort of evenly spaced around the memory chips, whereas this card sort of just ditches that in order to put two phases down here. So that's a thing. Other than that, I mean, we've got MSVDD coming into the core from both sides, vCore coming into the core from both sides. This is standard RTX 3090 stuff. The reason this is done is it effectively gives you a much larger power plane cross-section, because, if you have a piece of copper going like this, then like you've got a cross-section like that, and then you've got a cross-section like that. So effectively you've sort of doubled the cross-section then compared to if you were trying to squeeze all of the current into the chip from one side. This means that you get less power losses in the power plane, which is very useful on something like a 3090, which pulls absolutely stupid amounts of power. So anyway, that's what's going on with the VRM layout. In terms of the controllers, we're looking at a bunch of UP9511s. Now, I've heard a lot of people blaming the UP9511 for making EVGA's FTW3 have like power draw issues, which to me is completely absurd because the UP9511 doesn't handle the power balancing. That's not what it's for. Or like, it shouldn't be doing that. So like the thing with the UP9511 is this is an 8-phase voltage controller. It goes up to 600 kilohertz switching frequency, and it's completely analog, which is like, so the bad news with analog voltage controllers is you can't control them with something like an Elmore EVC2. The good news is you can tweak everything. Like you can tweak all of their operating parameters just using like potentiometers and basically just potentiometers. you really don't need much more to like completely reconfigure something like a UP9511. You want to change the switching frequency, you just have to adjust the resistance on one of the pins on the chip. You want to change the V droop, you just change the resistance on a different pin. Some of the pins will be multifunction, so you'll have to check the data sheet. But the 9511 also has a public data sheet, which is really great if you're going to be doing a bunch of modding. Is just like so I really like this chip as it's super easy to mod. Yeah, I don't know why the FTW3 has power draw issues. I wouldn't blame the 9511 for that. Like, admittedly, this is technically the cheapest voltage controller you can get on a 3090. And it probably doesn't do as good a job in terms of voltage regulation as, say, the monolithic power systems chips or the international rectifier chips. But it should be fine. Like, it shouldn't cause the card to power throttle, because it literally doesn't handle that. Like, that's not the UP9511's job. I mean, well, no, that's not entirely true. The UP9511 will, like, restrict how much power is going through each of the phases in order to protect the power stages. It doesn't, like, this chip has no idea what's going on with these shunt resistors. That's not its job. That's the job of the US5650. So the 9511, like, if the card is bouncing off the power limit, that's not the 9511's fault. That's the, like, something else on the card having a problem. So yeah, from that perspective, I don't see a problem with this chip. It's very modifiable, but also it's kind of like as it's basically as low end as it gets for voltage controllers on 3090s. Not that it'll really affect you in day-to-day usage. So anyway, so we've got a 9511 for vCore, we've got another 9511 for MSVDD, and then another 9511 for the memory rail, because, well, it's compatible with every, like, why, like, it's the low, like, why would you use different chips if you can just use one for everything? In terms of power stage configurations, so the vCore one, I believe, is running 8 phases, but into 10 power stages, which is just an NVIDIA thing and super awkward, and I really need to get my hands on an NVIDIA card to, like, check how like the voltage controller handles that. I suspect that it just ends up doing some kind of weird current steering thing to run twice as much current through 2 phases that are sharing a PWM line. So you might have, like, or actually might be something like you've got 4 over there, so you could have, like, this power stage, and, well, actually there's not really any reason to do it that way. Could do this, those would be 2, and then you'd have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so you could have something like that, where basically you have 2 oversized phases, and then the rest of the VRM is regular sized, and then the controller just kind of needs to be set up to push more current through the 2 oversized phases, which they should sort of naturally do, because they'll effectively have a much lower inductance than all the other phases in the VRM anyway. Yeah, so that is just like an NVIDIA VRM configuration thing that I still don't know exactly how it works. It's probably the thing. Like, that's one of the main reasons I'd like to get my hands on a higher end NVIDIA GPU someday, is to just get a chance to see, like, what does it do with the PWM signal? Like, it probably just runs the 2 power stages at the same time, in which case, yeah, you just get, like, a weird imbalanced sort of phase configuration. And it's still ultimately an 8 phase with, like, an awkward current distribution. Theoretically, it should still get, like, and which should, like, assuming the current is still shared evenly between all of the power stages, you would still get the benefits of having those extra power stages. So you'd still get the higher current handling capacity. But yeah, so we've got 10 power stages on vCore, so I'll put 10 PS, and I'm gonna go with the idea that this does actually increase the current handling capacity, because otherwise, why would you be doing this? Yeah, so that's what's going on with vCore. Then the MSVDD is just a straight up 6 phase, nothing weird going on there, because the 9511 goes up to 8 phases, so, you know, you can run it as 6 out of 8 phases, and that's just fine. Though I guess Zotac might have simplified their GPU, like, if Zotac wanted to, they could have simplified their VRM, like, design for the vCore by just running it as a 5 phase instead of an 8 phase. But without the card in hand, it's impossible to tell. Because I do know that there are NVIDIA GPUs where you just have uneven phases, which is super weird. Anyway, and then memory power is just a 4-phase, so the 9511, of course, has no issues running that either. So we've just got 4 phases with 4 power stages as well. So I guess 4 PS and 6 phase / 6 PS. So that's what's going on with the voltage controller configurations, at least as far as I can tell. And for the actual power stages, we are looking at a bunch of NCP 21 to, no, 25, 21, 60s. Yes, so these are 60 amp DR MOS components. They have a thermal warning system, but no other smart functionality whatsoever. So basically, they'll tell the controller, hey, I'm overheating, you should probably do something about that. But as far as like current monitoring or anything like that goes, the controller has to handle that itself. I wonder if we can see the current now. Oh, no, you can. Yeah, you can kind of see the current sensing circuits. Oh, no, you can really see it. Yeah, so, or at least you can see part of it. You can see we have like a trace going from the inductor. So the UP9511 uses DCR current sensing. So it basically uses the resistance of the inductors to like measure the current flowing through the inductors, and that gives you current monitoring on every single phase. Yeah, and so the NCP's, you know, dumb 60 amp DR MOS components, they're reasonably efficient, actually. Actually, I don't know how they compare. I didn't compare the graphs for these against a bunch of other power stages. It's been a while since I've done a 3090. Like, they're not on par with, say, the smart power stages that you see on some of the high-end cards, but these are not the worst. Like, the lowest end power stages that you'll find on a 3090 are somewhere in the, like, 50 amp current, like, nominal current rating, though there's generally not that much of a difference between the 50 amp parts and the 60 amp parts, so yeah, the more important part is that this does have 10 power stages, which is more power stages than the minimum specification. The minimum specification is that you have an 8-phase V-core, so Zotac has increased the current handling capacity by just putting more power stages in parallel. And the end result of that is that the VRM sort of like power stage efficiency, we can't, like, I'm not going to account for power plane losses, no real practical way of doing that. At 1 volt output voltage and 500 kilohertz switching frequency, the VRM would produce, well, pushing 200 amps into the core, the VRM would produce about 18 watts of heat, which is kind of a lot, honestly. For 200 amps output, especially at 1 volt, you can get power stages that'll do a much better job than that, but at the same time, like, this is a Zotac card, so I don't know what you expect. 300 amps output. And this isn't bad. Like, this is totally manageable. That's less than 2 watts per power stage, so it's not a catastrophe. 300 amps output, it'll produce about 31 watts of heat, which is still very manageable if you have airflow over the VRM. And then 400 amps output, we're looking at about 50 watts of heat, at which point it really depends on the cooling system. This is still very, like, this is coolable, but you actually, like, depends how the VRM is getting, you know, how the VRM is being cooled. And then for 500 amps output, at this point, I think we're well into, like, extreme overclocking territory in terms of current draw. Because the thing is, I still don't know what the power draw distribution between, like, core voltage and MSVDD is on 3090s. So I don't know, like, I'm pretty sure in order to get 500, like, even 400 amps, you might be looking at extreme overclocking, which this card's not really meant for. But at 500 amps output, this VRM would produce about 78 watts of heat, which I wouldn't recommend taking this card on LN2. Like, you just shouldn't. So, yeah, and then, of course, these are nominally 60 amp parts, so 600 amps on a 10 power stage VRM with these is kind of like, don't do that. Like, you don't do that. Bad idea. As you'd be looking at close to 100 watts of heat output or more, and that's well into the territory of, like, there's no real practical way of cooling that, except maybe if you water cooled the VRM, at which point you should probably just consider getting a better 3090 in the first place. But yeah, for, like, day-to-day usage, this is a totally, you know, like, it's a nice upgrade over the bare minimum. Like, this is a nice upgrade over a reference card, PCB. Is the way I'm looking at it. Like, yeah, it's not going to compete with a Strix or a Kingpin Edition or a Hall of Fame, but it's also not meant to, because or at least I hope like Zotac doesn't think this is supposed to compete with those, because like the parts aren't here for that. But yeah, so that's what's going on with VCore. MSVDD, if I'm not mistaken, MSVDD reference specification is actually a 5-phase. So Zotac, like Zotac has made some, minor upgrades around the card. And anyway, MSVDD is a 6-phase. So 1 volt output voltage and 500 kilohertz switching frequency again. There's a decent chance they're actually running the power stages at 300 kilohertz, considering that they're running UP9511s. But yeah, like, well, I'm not sure. Like, you'd have to but like the 500 kilohertz is a worse, like, is going to give you worse efficiency than 300 kilohertz. So I'm going to assume that they're at 500 kilohertz because I'd rather like underestimate the card than overestimate the card. Yeah, that's the correct way to use those terms. So 120 amps output from MSVDD, and again, I don't have any idea how much current MSVDD is supposed to pull. You'd be looking at about 11 watts of heat, which very manageable across a 6-phase VRM. 180 amps of output current, you'd be looking at about 19 watts of heat, at which point, depends on the cooling system. And then 240 amps of heat, 240 amps output current, it's going to produce about 30 watts of heat, which is like, yeah, that's a bad idea. Right? So at that point, we're getting into the sort of like this again, I'm assuming is like LN2 overclocking territory, and not really, like, it's just not what the card is meant for, right? Also, you're going to be looking at like 5 watts of heat per power stage, which is a lot. Like, it's, in line with what you see for 400 amps on the VCore VRM. And like at this point, you'd be looking at like, that would be 240 watts of output power on just the MSVDD rail alone. If you factored in the power losses from the VRM itself, you'd be looking at like 270 watts of MSVDD power draw, which is just like, yeah, that doesn't sound very realistic for a card on any kind of ambient cooling system. Because MSVDD is not meant, like, MSVDD is a smaller power rail, has less phases because it generally doesn't have to push as much current as the core rail. So if your MSVDD is pulling 270 watts, what's the core pulling, right? And you'd be probably looking at a card pulling close to around 700 watts at that point, and it's just like, okay, that's definitely like extreme overclocking territory, and so not really a concern for VRM. That's not really a concern for a card that's really not meant for that. At the same time, it would still do a better job than the reference designs, because it is just generally like, and basically with the exception of the voltage controllers, because, well, I'm not sure that the reference design from NVIDIA specifies if you have to use a 9512 or a 9511. I would assume it doesn't, because the 9512 is basically a slightly modified, is a slightly upgraded 9511. So I would assume that there's no real issue with using a 9511 instead of a 9512. And so, yeah, in general, this is just a minor upgrades to the reference design across the board. And anyway, so yeah, that's the MSVDD there. And then memory VRM, we're going to be 4-phase, which is on, like, that's what the reference specification is. You're supposed to have a 4-phase memory power. 40 amps output, it'll be producing about 4 watts of heat at, 4 watts of heat, and that's at 1 volt, 500 kilohertz. However, of course, GDDR6X does not run at 1 volt, it runs at 1.35 volts. And theoretically, if we try to scale this up according to some other power stages, unfortunately, the NCP 252160 documentation doesn't include any kind of how the power efficiency changes based on what output voltage they're at. But based on some other power stages, at 40 amps output at 1.35 volts, you should be looking at around 5 watts of heat, which is still, in line with what you'd see on most other 39, on basically all 3090s. So really nothing to complain about there. 80 amps output, which I'm going to say, there's no way the memory pulls 80 amps. Just no way. I refuse to believe that. Now, admittedly, NVIDIA's memory rail also powers some of the memory controller, not all of it. Like, the MSVDD rail is sort of the interconnect, powers the sort of connection from the memory controllers to the core. But yeah, VMem powers like the PHY, and then I think it's pronounced Phi. But like the actual physical, like the part of the memory controller that connects to the actual memory chips, like that runs on VMem because it has to, because the signals from the memory are using VMem as well. But yeah, anyway, like, so the memory controller does pull some power, but like the memory rail is not going to be pushing more than 80 amps. Like it should land, even with a heavy overclock, it should be maxing out somewhere around 60 amps. But let's say you somehow got it to pull 80 amps. It would produce about 7 watts of heat on 1 volt output voltage with 1.35 volts. It should be somewhere around 8 watts of heat. So not really a huge difference. So yeah, that's the power delivery, and it's basically a slightly upgraded reference design with more power connectors. I'm not really. I mean, well, the thing with NVIDIA cards and having 3 8-pins is that the 3 8-pins do actually allow you to do allow the manufacturer to ship the card with a higher power limit BIOS, right? Because I'm pretty sure NVIDIA won't let a manufacturer put a like 600 watt BIOS on a card that only has 2 8-pin power connectors, even though like the 2 8-pins would totally handle that. Like they really will. I mean, you probably want a good power supply at that point, but you can do 600 watts of GPU power draw in just 2 8-pins. That's not really an issue. The thing is, NVIDIA won't let their board partners ship that, like, power limits that high on those cards. Like, they won't even let you ship a card with a 450 watt power limit on 2 8-pins, I don't think. So having the 3 8-pins here is sort of like, in order to get like a higher power, like in order to be able to ship the card with a higher max power limit, you just need extra power connectors, because otherwise it's not getting through the NVIDIA PCB approval program. Or more like, you're not going to get to, like, NVIDIA won't approve your high power draw BIOS for the PCB. So, yeah, that's what's going on with that. Like, these aren't really super necessary, but like, yeah, if you want to have a high power limit, you just kind of have to have them. Because NVIDIA is not okay with not having that many 8-pin power connectors. Anyway, so yeah, this is really from like a power handling perspective, like from a power delivery perspective, this is just slight upgrades to a reference design, and that's, not bad. Like, I don't really see anything to like complain about massively. What's interesting, so that's sort of the power handling side of things. Now let's talk about the capacitors. So for output filtering, we have 1200 microfarad capacitors of unknown manufacturer. I have no idea who this like model number, I think, is probably or part number. Like, I don't know who this belongs to. No idea. Same goes for these. Like, these look like they're probably from the same manufacturer, but obviously these are sort of for 16 volts because they're on the high side. These are 2.5 volt capacitors. The interesting thing with Zotac cards is Zotac really likes to use 1200 microfarad capacitors, whereas most other manufacturers will go with like 820 microfarad capacitors. And there's no downsides to this as far as I'm concerned. At the same time, I don't think it really makes much of a difference. But it is worth noting that, yeah, Zotac likes to use higher capacitance capacitors for their output filtering. And then on the input filtering, we've just got 330 microfarad caps, which I think are also slightly more capacitance than what you'd normally see. A lot of the time, your input filtering is going to be using 270 microfarad capacitors instead of 330s. No real downsides to that either, as far as I'm concerned. Like, yeah, like more like, yeah, I don't really see anything to complain about. The slight increase in capacitance might mean, slightly better input filtering. And with the input filtering, so it sounds like, I think a lot of people, when I say input filtering, a lot of people probably think, oh, it's for filtering the power coming in from the power supply. No, that's not what these capacitors are for. No. These capacitors are here because when the GPU core decides to suddenly pull a giant amount of current, thanks to the input filtering inductors, there is basically the point of these inductors is to suppress the current draw spike from the VRM from going outside the card. That's the point of these inductors. Now, if you're going to be suppressing that giant current draw spike, what's that going to do to the voltage on the actual, like, on the VRM side of the input filtering? Well, it's going to send it, like, it's just going to send it plummeting down, because the VRM's basically like, hey, I want a bunch of energy, and the inductor over here is like, well, you can't grab it that quickly. And so the VRM is going to do its best to pull it from before, like from, after the inductor. And that's why we have these bulk capacitors basically for each phase. Because when that sort of power transient happens, instead of, the voltage, so when the voltage starts to dip, when the VRM tries to grab all that energy, it'll just grab it from the input filtering capacitors. So that's what those are there for. If you don't have those, it can lead to really, really bad output voltage regulation. And in some cases, these can actually also, like the configuration of these can somewhat affect coil whine, though generally it won't. It's like they're not supposed to do that. That's not their primary purpose. Their primary purpose is to make sure that the VRM has plenty of power available on sudden load transients, because if they're not there, then your input voltage is going to massively drop, and then your output regulation is just going to become really, really, it's going to become really difficult to maintain output voltage if, your input voltage is falling down at a very rapid rate. So that's why we have these. And yeah, it looks like Zotac has slightly increased the capacitance on those. They've done the same on the output filtering, which same idea is just like if the core suddenly grabs a bunch of current, again, these inductors, they limit how quickly you can, how quickly the core can pull current. So initially the core is going to be pulling all of its current from these capacitors. And so the extra capacitance there can help with voltage regulation a bit. And we've got an input filtering capacitor for every single phase, which is what you'd expect to see on a 3090. This is standard 3090 things. And then output filtering, we've basically got a bulk capacitor for each phase as well. Higher end cards will actually go for more capacitors than that. Also, higher end cards will replace the through-hole capacitors with SMD polymers like these, because SMD polymers have less ESR and less ESL, and that means that it's easier for the energy to both get stored into the capacitor and released from the capacitor when it's suddenly needed. That's what's going on with those. On the back of the card, we have this lovely thing, and so that is just a sort of vanity cover for a bunch of SP caps. All this is doing is covering up a bunch of these, and I don't know what exact spec the ones under there are going to have, but SP caps are great for power. The SP caps are really, really great for output filtering. So I have I don't think this is necessary, but, I'm not going to complain about more SP caps on the card. There's just, I don't know how many SP caps are in there. It's probably 6. Yeah, probably 6, maybe 4. So not really that many of them. High-end cards like the Kingpin Edition, the Hall of Fame, or the Strix 30, or a Strix PCB will actually go for an all SMD polymer they're going to be using all SP caps or pause caps in some cases. The main thing is you're gonna have the main thing with the SP caps and the pause caps is just the style of packaging that they have has much less ESL and ESR. So regardless of if they're aluminum polymers or tantalum polymers, as long as they're in this style of packaging, they just have a ESR and ESL, well, mainly an ESL advantage over your through-hole capacitors, because you can actually kind of get similar ESRs for through-hole capacitors. Though you can get SP caps down to 3 milliohms ESR, whereas through-hole capacitors bottom out at around 4.5 as of very recently. It used to be that you couldn't get anything with lower ESR than 5 milliohms. So anyway, this is just a fancy cover plate for a couple SP caps, and they probably make some difference to the voltage regulation, but considering this is not going to be on par with the likes of a Hall of Fame or a Kingpin or even a Strix card. Right, this is still mostly relying on the fact that there's a lot of through-hole capacitors in the VRM, and it's not just SP caps for the output filtering. Anyway, behind the core, we've got 330 microfarad SP caps. So this is above the minimum specification from NVIDIA, right? And the minimum specification from NVIDIA is that these are actually 220 microfarads. which, again, more capacitance is generally more better unless you're giving up ESR or ESL for it. I can't imagine that they've, like, increased the ESR on these, so I'm not going to say there's anything wrong with that. However, what is very interesting with the capacitor configuration behind this core, because, like, the SP caps are just kind of a normal thing that you see on 3090s, is the fact that Zotac has actually not left any multi-layer ceramic pads unpopulated. Like, normally this middle capacitor on a lot of cards doesn't exist. It's just not there. And the same goes for a lot of these, like, smaller capacitors. Now, I'm not sure which specific ones are normally left out because I don't pay that much attention to this. And even if I did, it would be incredibly difficult to remember which exact capacitors are the ones that most manufacturers don't bother including. But it is interesting that Zotac has actually fully populated all of the capacitor positions behind the core, because that's not something you normally see. And that can slightly help with, again, voltage regulation on the GPU. So yeah, I'd imagine if you took an oscilloscope to this card and you tried to compare it against the reference design, this should generally come out with slightly better voltage regulation than a reference 3090 PCB design. So that could lead to ever so slightly better overclocking headroom. So yeah, like, just in general, this is basically a very slightly upgraded reference card. We've got slightly more power stages on both VCore and MSVDD, if I'm not misremembering the minimum phase count for MSVDD. We've got more capacitance than you'd normally see, a somewhat better mix of capacitors than what you'd normally see, right? Like, the SP caps seem to be slightly upgraded in terms of how much capacitance they have. Then they've actually populated all the multi-layer ceramics behind the core. The power stages are 60 amp parts instead of 50 amp parts, so slightly better if it... Well, I still think, if I remember correctly, those 50s are basically the same performance as these 60s, but, like, there is more of them. And then the only real thing you could maybe complain about is the fact that this is using UP9511 controllers. But if you're into hard modding, which this doesn't really make sense to do that on this card. Like, again, if you're going to be serious, like, if you're serious about overclocking a 3090, get a Kingpin edition, get a Hall of Fame. If you can't find one of those, then I guess get a Strix. But yeah, like, if you ended up with, like, I guess if you found one of these several years in the future cheap on eBay and you wanted to mess with a car, like, and mess around with volt modding one of these, then the UP9511s make that really, really easy. So I kind of like them for that, because they are extremely easy to modify. So yeah, that is it for this PCB breakdown of the RTX 3090 Amp Extreme Holo from Zotac, and yeah, it's a stretched reference card, which is not necessarily a bad thing. So yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTuber merch. Both the Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you'd check them out. And yeah, that's it for the video. Thanks for watching, and goodbye.